All right, we're live. Okay, so the law of conservation of energy. If we're looking at energy, the law of conservation of energy states energy is never created nor destroyed, just transformed into other forms of energy. So the energy before reaction has to equal the energy after reaction. You guys have all had chemistry. Malik, you've all had chemistry, and you guys know the reactants should equal the products. And so when you took chemistry, remember balancing equations? One of your favorite things, the amount of elements before have to equal the amount of elements after. It's like that in physics too. All right, except we're looking at energy. And so yet if energy is added or removed from a system, the total amount of energy has changed. This can only be accomplished by external forces, which is work. If energy is added, positive work has been done on the object. If energy is removed, negative work was done on the object. Therefore, work must be accounted for in our equations. So we've been working like with just potential energy and just kinetic energy. Now we have to put it together. Potential energy has to equal kinetic energy, or potential elastic has to equal potential, or potential elastic has to equal kinetic, and how those energies are related before a reaction and after a reaction. So on this front of the page, you guys have some examples right here that you can look through, and I know a lot of you will look at that, think it's gobbledygook, and you're going to want to move on to do other things. So I'm going to force you right now, we're going to go over them as a class, because I want you to understand how these equations work, and that they're not as scary as they initially appear. Okay? Okay. All right, so the first one is looking at a spring. So we have a spring. The initial part of it, the spring is compressed. It's a 2 kilogram box sitting in front of it. In the latter portion, the spring has been released. We have our 2 kilogram box is now on the move. So in the problem it states, a 2 kilogram object compresses a spring 0.5 meters. So we've been squished up here 0.5 meters. If K equals 72 Newton meters, so what's K again? K is our spring constant. How fast is the object going after the spring is released? So we want to know what is the speed of our spring after, or speed of our box after we've released the spring. So how are we going to find that? Oh my goodness. So let's take a look at our system. What is the type of energy that we have at the beginning of our reaction? Potential? Potential elastic. So we have a peel. Very good. So potential elastic. We've got to address work. Work is either going to be positive, negative, or zero. So there's some work happening in this equation, maybe. And that's going to be equal to our equation afterwards. And what's happening after that spring is compressed? What's that box doing? It's flying. So what kind of energy is that? Kinetic energy. So potential elastic energy plus or minus work is equal to our kinetic energy. So let's write down what we actually have in those equations. Potential elastic energy is 1/2 kx squared plus or minus our work, and the formula for work is force times distance cosine theta, and then our kinetic energy 1/2 mv squared. So let's go ahead and start plugging in our numbers based upon what we know from our picture up here. We have 1/2. They gave us our spring constant, which is 72 newtons per meter. The distance of compression is x. So it tells us in the problem that it was compressed 1/2 meter. So 0.5 meters squared. Now let's take a look at our work. How much work is being done here? Was there a force applied? When you walked into the room, the spring was already squished, right? We didn't see it being compressed. We just know that it is compressed. So in this case, and it also too, once it releases the force, the compression here is being transferred over here. So our work in this equation, since there's no outside force, is 0. So then we don't have to worry about distance and cosine theta. You will have examples, though, where work actually does have a value, and we'll point those out when we get to them. All right, and then 1/2 times the mass of our box, 2 kilograms, and then we're solving it for velocity. So we've just taken our tiny equations, put them all together, and made one ginormous equation. So let's go ahead and work this one. You've got 1/2 times 72 times 0.5 squared equals 1/2 times 2v squared. Since you guys already have it on here, I'm going to cut to the chase. You're going to end up, after you do all your math, with 9 meters squared per second squared is equal to velocity squared. When you go and square root that, your final answer is 3 meters per second is your velocity. Now I know I skipped a lot right here, but once you guys plug those numbers in, it should work out to 9. Okay? So let's do another problem. The next one we're looking at is a box being moved. So we've got our box, how much is it weigh? 3 kilograms. How much is it moving? How much force was applied? 8 newtons. And so a 3 kilogram mass that rests on the ground is pushed by an 8 Newton force for 4 meters. How fast is the mass going afterwards? So a box at rest, what kind of energy is that? Potential energy. So we have potential energy plus or minus work is equal to after, well, the box is moving, so we have kinetic energy. Good. So kinetic energy. So let's go ahead and put in our formulas. Potential is mgh plus or minus our force, our work, which is FD cosine theta. And then kinetic energy is 1/2 mv squared. So our box weighs in at 3 kilograms. Gravity is 10 meters per second squared. How high up is it? Where is it? It's on the ground, so it's 0. So actually, I just made you do that for nothing. So it's 0 meters up off the ground. Our potential energy at the beginning here is actually 0 since it's sitting. All right, our work. How much force was applied? 8 newtons. The distance, 4 meters. And then cosine theta are not 180. Our force and distance are in the same direction. So the angle between them at the same is 0. So it's cosine of 0, which we know if we punch in cosine of 0 into our calculator is actually 1. Now is it positive 1 or negative 1? Positive 1. So when I put plus or minus work, now I know that it is plus work. If it was 180, it would be negative work. But since they're in the same direction at 0 degrees, then it is positive work. All right, and that is equal to 1/2 times our mass again, which was 2 kilograms, and our velocity squared. Okie dokie. So if we work our numbers here now, 3 times 10 times 0, what do we get? 0. So we can just ignore that one, really. 8 times 4 is 32, and 32 times cosine theta, which cosine of 0 is 1. So we're going to get 32 Newton meters. And 1/2 times 2, I'm sorry, it's not 2. Why didn't y'all correct me? That should have been 3 kilograms. 1/2 times 3 is 1.5 kilograms v squared. So when we go and calculate that one out, we're going to divide both sides by 1.5 kilograms. You're going to end up with 21.3 meters squared per second squared equals v squared. And the square root of 21.3, 4.6 meters per second equals velocity. So, again, I skipped a lot of the general algebra stuff in there because you guys have your stuff and you can go back and you can do that and get those numbers on your own. All right?